everyone. This is our first video together, and it's the beginning of Chapter 1, and Chapter 1 is called Functions and Graphs. And the first section that we're going to look at together is called Modeling and Equation Solving. So in your notebook, I want you to write down the chapter title up here, Chapter 1, Functions and Graphs, and the section title 1-1, Modeling and Equation Solving. Basically, what this is going to cover are the three different types of kind of viewpoints we're going to take as we go through the year and look at the content that we're studying. So we're going to talk about three different models that we can use in order to help us solve the equations that we're going to see as we go through the, especially the pre-calculus part of the course. The first is a numerical model. And a numerical model is represented by either numbers or data, and those numbers and data are analyzed to gain insight into phenomena. That's really kind of a beefed up definition for what this representation is. Something simple that you could make a correlation to that you could put in your notes is something like, sports standings, baseball standings. They're represented in a table. And that table is considered to be numerical data. If you're collecting data in a science class data. Information that you can use in order to write an equation from or put a graph together from, that would be considered to be numerical model information. So numerical models will be one type of model that we're going to see as we go through the course. The most basic, definitely, because there's no picture or no equation put to it. It's just a set of data presented to us. What I'm going to do is I'm going to erase this screen, and you're going to see this happen as we go through these on a routine basis. I'm going to erase the screen. Make sure that you get in what you need to get in your notes from this screen, and then I'm going to scroll to the next screen. So we'll do the erase. We'll scroll down, and remember, as we go through these videos, you can stop and pause, you can rewind and things like that in case you're missing something or you can't keep up or just need to hear something again. We're going to look at an example of something that's represented by numerical data, and this example says the table below shows the growth in the number of prisoners incarcerated in state and federal prisons between 1980 and 2000. So those dates are important. The question being asked of us is the proportion of female prisoners over the years increasing? And then once we answer that, how would you determine your answer? So this is definitely a representation of numerical data. It's set in table form. And it's just basically a set of numbers. We need to look at the table in order to answer the question that's being asked of us. We may not need all the information, and that's the biggest thing about numerical data. You might have to sort through it before you make a decision on what the best piece of the data is to use for the questions being asked. So the proportion of female prisoners over the years increasing. How would you answer that question? How would you go about responding to that question? Take a second. You can pause the video, take a second to think about that. Look at the data table and figure out how you might answer that question. Is the proportion of female visitors over the years increasing? So hopefully you either paused the video or you took a little time to think as I paused briefly there. But if we want to figure out if the percentage or the proportion of female prisoners over the years is increasing, we really don't need the column of the male prisoners. We're really looking at the number of female prisoners in any given year to the total, that comparison. So hopefully you guys were thinking that in order to figure out the proportion, we've got 12,000 out of 316,000 were female prisoners, which would leave us with, if you did this on your calculator, about 0.038 38 thousandths, which is 3.8%. So 3.8% of the prisoners in 1980 were female prisoners. If you did this for the rest of the data, and I would say that would be a way that you can check to see if the percentage, the proportion is increasing, we would get 4.4% for the 1985, 5.5% for 90, 5.9% for 95, and 6.7% for the year 2000. Based on that information, it would be good to be able to draw a conclusion. So I would say that, yeah, over the years, the proportion of female prisoners is increasing, and it might actually promote discussion with looking a little deeper at the actual percentages that we have, you know, why percentages were the way that they were in certain years, so on and so forth. So I could see something like this, the math being used in something like a history class. If you had to analyze data, you could look at it in a science class if there was science data that had to be analyzed that way. So there are definitely connections that you can make with other areas. I guess what we did with the math there actually answered the second part of this question. How would you determine your answer? If there's someone in the room who looked at this a different way, I'd love for you to jot that way down, and I'd love for you to bring it into class so that we can all talk about it. So I'm going to move on. I'm going to erase this. And again, as I go through this, if you have questions on any of this material, you need to write those down in your notebook. You can email me those questions. You can post them on Edmodo. You all should have joined the Edmodo account. If you haven't done that, I'm reminding you to do that now. But be ready to talk about the things that, you know, you might have questions about. You could even rewind to see if you could answer those questions yourself. If not, definitely bring them into class. So that takes care of the numeric model. The next is the algebraic model. And the algebraic model is something that you guys are really familiar with. You've been using it a lot as you've gone through your previous courses. These are going to be the models that are formula-oriented or equation-oriented. So we're relating variable quantities associated with the phenomena being studied. We can use equations or these algebraic models to generate numerical values. So we can work backwards from an equation. We could actually make our table and present our numerical data. Sometimes it's easier for the general public to read some things in a table that came from an algebraic model to get understanding a little bit deeper. So they come hand in hand, and that's what you're going to see as we go through the course. How do these methods that I'm introducing to you here work hand in hand and are kind of intermingled so that they can all be used depending on the situation that's presented at hand. The second example that I have here is really, really straightforward, but it's an example of something that would represent an algebraic model. It says a pizzeria sells a rectangular pizza, 18 inches by 24 inches pizza for the same price as its large round pizza, which measures 24 inches in diameter. So I can already see that there are going to be some important pieces here. So this is rectangular, 18 by 24, and this is round, 24-inch in diameter. If both pizzas are of the same thickness, which option gives the most pizza for the money? So it kind of sounds like a cat problem, doesn't it? In order to solve this, we want to set up an equation, and that's the algebraic model that we're using. If we're looking at the rectangular pizza, I think we're looking at the area. You guys are definitely adept math students here, so I might even suggest that you take a second and try to do the comparison, pause the video, and I'll do this out. You can kind of check your answer against my work in a couple minutes. The key here is that if we want, we're looking at the same thickness. We know that, I guess I wrote down area, but I suppose that we could be really specifically looking at volume. Since the thickness is going to be the same, we can take that dimension out, and if we compare the areas, then we also can figure out which is going to be the better deal. So if we look at the area of the rectangular pizza, we know it's length times width. I don't know why I wrote the approximate signs there to give me a little leeway here at the beginning of the year. We know that the area is going to be 18 by 24, which will give us 432 square inches. So we have 432 square inches of pizza with our rectangular shaped pizza. The circular pizza, the round pizza, which we're kind of used to seeing, remember, is pi r squared. So we've got a diameter of 24, which means our radius is 12. And if we do this out, this gives us about 452 square inches. So by a bit, the round pizza is going to be a better deal. Now, I technically didn't bring the thickness into play because the thickness was the same in both pizzas. However, if the thickness was different for any reason, we would have to be assessing the volume, which really turns this into a rectangular prism and turns this into a sphere. Whoops, I wrote area again. This would be volume. So that would have to come into play. But the fact that we're using a formula is demonstrating the idea of the algebraic model. The math isn't hard there. I just want to be able to have you guys understand what an algebraic model actually is. So I'm going to erase this again, write things down, write down your questions. Feel free to email them to me or post them on Edmodo, and we'll keep cruising along here. I just have a little blurb up here. Ultimately, scientists and mathematicians want to fit an algebraic model to numerical data. So we want to fit the algebraic model to the numerical data and analyze why that connection actually works. It's often helpful sometimes to look at a picture, though. So that brings our third piece in, which we consider to be the graphical model. When we started using graphing calculators in classes, it was amazing how much more of a connection some students made because they are those visual learners. And that graphical model is another way for understanding to occur. So a graphical model is a visual representation of a numerical or algebraic model that gives insight. So this helps us see into the relationship between variable quantities. So we're looking at insight into the relationship between the quantities within either the columns from our data table or the variables, independent and dependent variables in our algebraic model. So we'll quickly look at a graphical example and then delve into a couple of just skill-based things that I need you to understand before we move into some of this. So this page wasn't too tough, very definition oriented. But we're going to go back to that table we looked at earlier in this third example. And this example says, earlier we found that the percentage of females in the U.S. prison population has been growing. We agree to that because we looked at that proportion. Model this growth graphically. So we want to model that growth graphically and use the graphical model to suggest an algebraic model. So what we know is this. Let me just flip back to the numbers that we had. We knew in 1980, 3.8% of the prison population was female. 85, it was 4.4%. 1990, 5.5%, 1995, 5.9%, and these values are all coming from what we looked at before, 6.7%. So we want to take, this is numerical data, we want to put a graph to it, and then from that graph get an algebraic model. So what could we use that you've worked with in the past in order to get a graphical model of this that's going to help us get to an algebraic model? Think about that for a second. What have you used in the past? What type of graphing have you used in the past to help you possibly make these connections? Those of you who were thinking that you might want to draw a scatter plot are probably along the right lines here. If we can put this data into a scatter plot, we could put some type of a regression to the data points on the scatter plot, and that will give us our algebraic model. So I'm going to bring up the calculator. And you might want to take your calculator out with you here as we do this, and do this with me so that I'm just going to clear everything out of here so that you remember how to go about that scatter plot process. If we want to graph data on a scatter plot, we're going to go to the stat mode, and we're going to choose edit first. Now I have data in here from previous courses, so I'm going to clear that out. It didn't clear. There it goes. I'm going to go up, clear, and go back down. So I'm going to clear my first two lists because those will be the lists I'll use for my scatter plot. And the data I want to plot is the data that I just wrote on the video with the year and the percentage. So the first year was 1980. We don't want to put 1980 in because that would become the x coordinate of our point. I'm going to put the year 0 in. So 1980 is going to correspond with year 0. 85 is 5, 90 is 10, 95 is 15, and 2000 is going to be year 20. So in 1980, we had 3.8% of the prison population were female. Then we jumped to 4.4, 5.5, I think it was, let me get the numbers here again. I just put them down. 5.5, 5.9, and 6.7. So 5.9 and 6.7. Okay, so think about how you go from this data to graph the scatter plot. If you remember, go for it. If not, follow along with me closely. To graph the scatter plot, we need to make sure that our stat plot is on. So I'm going to go second in stat plot. Mine happens to be on from when I used it last. If it's not on, turn it on. And then I'm going to go back to, I'm going to go back to stat. No, I don't want to go back to stat. I'm a step ahead of myself. I'm going to hit zoom 9. And zoom 9 is going to give me my scatter plot. So that zoom stat is what's going to graph the data in those lists. So these are the 1, 2, 3, 4, 5 data points. This is our numeric data now put to a graph. It's only graphed as ordered pairs basically, and we want to see if we can put an equation to it. And that's where our regression is going to come into play. Sorry about that. It looks fairly linear, so I think I can get away with a linear regression. To get our regression line, we're going to go back to stat, go over to the calculate menu, and I'm going to choose number 4 for the linear regression. I'm going to enter it, and it gives me the information right there. Some of you may have some more advanced calculators than the emulator that I have here, so you may have to go through another routine to actually before you get to that point. But basically it's saying that y equals 0.146, 146 thousandths, plus 3.8 is the equation that will model the data that's there. So I'm going to go back and enter that. And some of you may have put it under y sub 1 because it's a small equation. I'm going to just enter it by hand. 0.146x plus 3.8. And if I hit graph, let me get it out of here. If I hit graph, you notice that that's a pretty decent regression line. We miss a couple of the points above and below, so it pretty much evens out. So this equation, that y equals 1.4 or 0.146 plus 3.8, this is our algebraic model. So that's basically what was being asked of us to do in that problem. Take a set of numeric data, get a graphical model to it, and then extend it to its algebraic piece. So really we combined all 3 parts there. What this algebraic model can do is it can help us look at any of the years in between those key years that were posted to us. If we go outside, it's not as accurate because we're taking information of excuse me, of data that was not in that original table. But it can definitely help us analyze for any of the dates between the starting and ending dates that we had. So you should definitely recall how to work with scatter plots on your calculator. I'm gonna move on from here. If you need to review that or ask me any questions about input, if your calculator is a little bit different, write yourself a note and we'll talk about that a little bit in class. Last couple things here, just for frame of reference so that as we move forward with solving equations and everything, we're all on the same page with remembering what we needed from our previous classes. This idea of zero factor property. This says, this is important, a product of real numbers is 0 If and only if, IFF is not a typo, if and only if, that means there are no exceptions, at least one of its factors in the product is 0. You've done this before with solving equations, and it is definitely a helpful concept in solving equations algebraically. I actually just talked about this with my calculus class and refreshed their memory on things. So we're going to look at a couple of things here just to get back in the swing of things. Find all real numbers x for which 6x cubed equals 11x squared plus 10x. So if you remember from any of your algebra classes, we always want to set our equation equal to 0 if we're working with something other than a linear equation. So 6x cubed minus 11x squared minus 10x equals 0 will be our jumping off point from here. When you work with solving equations, you always want to look for that greatest common factor first. And what we see in this problem is that the GCF is x. So that leaves us with 6x squared minus 11x minus 10 equals 0 as our second factor. We have two factors now, one factor and two factors. And I'm going to look to see if that quadratic factor can be broken down any further. And as I look at it, it can be broken into 3x plus 2, that quantity, multiplied by the quantity of 2x minus 5. Now what the zero product property says is that we can take each individual factor, the 3 that I have underlined in the problem, and we can set them equal to 0 to get the solutions to the problem. So that means x will equal 0, 3x plus 2 will equal 0, and 2x minus 5 will equal 0. Each of those solutions will give us an answer to suit our equation. So x equals 0 will come right off the bat. X will equal negative 2/3, and x will equal 5/2 will be the other two solutions. So you should keep this skill definitely close to your back pocket here because we'll be using it quite a bit when we solve equations. If you have any questions about that, feel free to bring them into class with you, please, because we need to make sure everyone is definitely mastered this idea. Example 5 says solve x squared equals 10 minus 4x and to use both an algebraic and a graphical method. It's a quadratic, so I'm going to approach the algebraic first. X squared plus 4x minus 10 equals 0. I'm going to set it up in descending order, setting it equal to 0. If I look very closely at this, the first method that I want to use, if possible, is the factoring method. But unfortunately, as I look at this, I don't see that this quadratic is factorable. So we could use quad form, I suppose, on our calculator. That would be cheating a little bit because we're not going through the whole algebraic process. But other than that, we're kind of stuck with using quad form in the long sense. So I'm going to actually let you go and do this one on your own to see what you come up with. Your final answer should be the following. Negative 4 plus or minus 2 radical 14 over 2. Make sure that that's what you get. If you have trouble applying the quadratic formula, then part of your responsibility is going to be to come into class and ask me about it in class. So once you get to that point, you've got the algebraic solution. We didn't do decimal approximations. I would prefer the exact answer, which means radical and fraction form, if we're not using this for application purposes. If I need to know that decimal for some meaning in the problem, change it over to a decimal. If not, then radical and fraction form is definitely the most accurate. This also says to use a graphical method. How would you do that? How would you solve this using a graphical method? We definitely need our calculator. So we'll pull that back up. I'm going to turn my stat plot off so that doesn't interfere with anything else that I do here. If we want to use a graphical method to solve this equation, I'm going to put it in the descending order that I had, plus 4x minus 10, and I'm going to look at that graph, so I'll zoom 6 it. Oops, the scatter plot is still there. I don't know why it's still there. Let's see, because it never turned off. All All right, that's better. So there's our graph. We don't see the entire graph, which I guess for this problem is perfectly fine because we're only being asked to solve it. If you needed information about a maximum or a minimum, in this case a minimum, you'd have to play around with your window a little bit. But what we're concerned about here are the places, the points where the graph is crossing the x-axis. Those are our solutions. Those are the answers to our equation. So just to refresh your memory, if you're doing this graphically, we're going to go to second calc and choose number 2. And that's going to prompt you for left bound and right bound, if you remember correctly. I'm going to focus on the leftmost solution first. So I'll cursor over to where I'm above the graph. That's the left bound for that 0. And then I'll go a little bit below the graph. And this is telling me that negative 5.742 x equals is going to be one of the approximate solutions to that equation. I'm going to also go over to the right one, second calc 2. Move in the direction of, now our left bound is going to be below this time. Whoops, I hit it too many times. I knew that I was going to do that to get it to come back. So I'm below the y-axis because the y value is negative. Hit enter, go above it, hit enter one more time, and that's going to give us x equals 1.742. So actually these two values that we get are the decimal equivalents to the fraction and radical form that we just did algebraically. Quick refresher on how to work graphically. You'll be asked to do both algebraic and graphical analyses of things. So again, if you have questions, please let me know in class the next time we're together. So that's it for this page, and we really only have one more little piece to get through. What I do need to make you aware of is a little bit of vocabulary and then just some understanding of the graphing calculator. So the vocab that we need to make sure that we sort out is the following. We're going to start off with A representing a real number, and that solves this equation f of x equals 0. 3 statements mean the exact same thing. The number A is a root or a solution of the equation f of x equals 0. The number A is a 0 of y equals f of x. And the number A is an x-intercept of the graph of y equals f of x. So when we're working graphically, we can make a connection to them being x-intercepts. An x-intercept really is the x value comma 0. So if we're looking for x-intercept form, we want to write it the x value comma 0 as an ordered pair. If we're working with y equals f of x, then the value that solves f of x equals 0 is considered to be a 0. And if we have f of x equal to 0 already, then we call them roots or solutions. So we'll use this language interchangeably depending on the situation that we're presented with. You've heard the words before, just wanted to bring them back to the forefront of your minds so that as we go through class and we use this vocab, everyone's on the same page. So write down, these definitions and come in with questions if you have anything about the wording that you're not sure about. All right, last page for us to get through. This is an important page to some extent, but I'm going to reinforce it as we go through the rest of the semester. It's important to understand that graphs, especially those drawn on our graphing calculator, can't always be relied on. And I say that because as great as it is to have technology, sometimes that technology doesn't always help us out as much as we want it to. So we're going to take a peek at 2 different functions. The first being, I'm going to bring up the calculator again. Let me erase what we had on here so we can have a clear screen. The first being this. Let me clear this out. 3 divided by, and I'm going to put the denominator in parentheses because there's more than one term, 2x minus 5. And I'm going to graph it. Whoops. Zoom 6. That always brings me to the standard viewing window. So here's the function. Maybe it's a function that you've seen before, maybe not. I'm not too worried about that because we're going to talk about some things. But what's going on here, ladies and gentlemen, is the following. This is 3 over 2x minus 5. I know with a little insight into this problem, and you guys will pick up on this really quickly as we move through this chapter, that there are some things that are happening here. F of x equals 3 over 2x minus 5. It's hard to really tell based on this graph, but there's definitely a gap here. And you just have to be aware of the fact that at a certain value, this function is not going to exist. We're not sure. It looks like these connect. They're really close to each other, like they might parallel each other, but they actually don't. So you have to have a little knowledge about your algebraic functions as well, and that's what a lot of this course is about, is analyzing these both graphically and algebraically, somewhat numerically as well, just to make sure you understand all the what's considered to be hidden behavior. So you can always rely on your calculator in order to get the answers that may be posed to you. The next one I'm going to put up, and if you write these in your notebook, that's perfectly fine. If you don't, it's not that big of a deal either. You just have to make sure that you understand what I'm talking about with this hidden behavior. X cubed minus 1.1 x squared minus 65.4 x plus 229.5. And that's equals 0. So if I want to solve this, this is what I'm putting in. And if I zoom 6 it, standard viewing window, this is what I'm getting. Now, this was a cubic function, which means there could be at most 3 solutions. But if for some reason I had asked you for the entire graph, this isn't cutting it, ladies and gentlemen. You need to see more of this. You need to see where the max and the mins are so that you can see the entire behavior of the graph. And that's what I'm saying about hidden behavior. This type of information would need a window change. So as we go through the course, you're going to have to pay attention to your calculators and make sure that they're presenting you with the information that you need in order to solve your problem. I'm definitely going to bring this up again, probably repeatedly in some of the sections, so don't worry about it, but it's just a heads up for what could be hidden on your within your functions from your calculator. Maybe as the calculators get a little bit better, they'll keep refining this, and we won't have to have as many hidden behaviors here, but we'll keep our fingers crossed. Maybe not in your mathematical career, but we'll see. So that honestly is the end of section 1.1. And I thank you for listening. I thank you for taking notes, and I thank you for writing down your questions, because those are really going to jumpstart our conversation in class the next time I see you. So as far as it goes, we're done. You can close your notebooks, and I will see you in class. Thanks again.